An important part of working with exponential functions is solving them. This is going to be heavy algebra.
Perfect.
Here we go. The main goal of these kinds of problems is to get the bases to be the same. So for example, you notice that this has a base of 3. It would be ideal to make this 9 have a base of 3 as well. Might I propose to you that we can do that? We can express 9 as 3 squared. And what happens is if we manage to get these bases to be the same, then the exponents are equal to each other. So we're only allowed to do the next step because the bases are the same. You might want to put that in your left column. If the bases are the same, the exponents are equal. Recall, of course, the original was 9. We express it in terms of the same base 3. So we end up with this problem, and it becomes a simple two-step problem from 7th grade. We divide both sides by 2, and we get that x is 3 over 2. It's up to you to decide if you want to go ahead and take this answer and plug it back into the x to see if it's true. I'll leave that up to you if you're interested. Here's another problem. Ideally, let's make these bases to be the same. I will do this problem 2 different ways, by the way. So because I know my power is pretty good, I'm going to make this 256 into base 4. That'll be 4 to the 4th power. Doing that, we get to set x squared equal to 4. And to solve for this, we have the square root. Square rooting would result in a plus or minus 2. So we do have 2 different answers. The 2 answers are a positive 2 or negative 2. Of course, it's up to you to also decide if both of these are answers or not. You would go ahead and be plugging them in one by one to see if they actually check out. An alternate way to do this would actually be to do this in terms of squares. So this is a bit more complicated. I don't suggest it, but in case if you run into problems where you are not too comfortable with your bases, I could express this 4 as a 2 squared. 256, I could express this as 2 to the 8th power. Now, based on properties of exponents, when I raise a power to a power, I just multiply them. So this is 2 times x squared. And then 8. Because if the bases are the same, which they are, it's equal to the exponents are equal to each other.
Perfect.
I would first divide by 2. And we end up with the same situation as before. 2 answers, plus or minus 2. Okay, so either way is fine. Just be aware. Well, may I suggest that there's only one power here, and it's this. And then I have this base of a 2, this base of a negative 1, and this weird looking base right here.
I think I need a hug.
So how about we go ahead and try to do as before, when you notice other problems, how there was only one term by itself, right? There was one term over here, one term over here. And same thing with the previous problem, there was one term by itself and one term by itself on the right side. This time we have multiple terms, so let's go ahead and eliminate as many as we can. I'm going to add 1 to both sides. That eliminates this. This is 1 over 1, and to get a common denominator for this, we'd multiply them both by 2. That results in a 1/2. But that still doesn't solve the problem of having the same base, because in one case I have 2 and the other one I have 1/2. Recall that a negative exponent switches things around across the fraction bar. So I propose to you that 1/2 could be made into 2 to the negative 1. And doing so gives us the same base. If the bases are the same, the exponents are equal. I have a quadratic, and I'm going to go ahead and move this over to the other side to make it into a standard quadratic form. At this rate in the class, there are expectations of algebra skills and abilities. This is a quadratic equation. There are multiple ways to solve for this. If you stand in need of assistance with how to factor trinomials of quadratic form, feel free to stay for office hours. But in this case, if we factor this out, I get x plus 1 times x plus 1 equals 0. And of course, if I separate these and solve, I end up getting the same answers for both, -1 and -1. So the answer just stands to be -1. If you were to put a -1 into this x and into this x, you would, and then check, you would see that this checks out. For your summary, we're going to go ahead and throw it back a bit to what we did in class the other day. Look up logistic modeling. How does it differ from exponential modeling? Is it a better model for population modeling? So take some time to think about that. They give us a function for an element that decays. When we talk about half-lives in chemistry, when we talk about radioactive dating, that we are essentially talking about decay, which is the opposite of exponential growth. It is modeled by an exponential model. In this case, we have an element that decays based on this model, where A is the number of grams present, T is the time in years, and they want us to know how many grams will remain after 900 years. So this is honestly a very straightforward problem where we just plug things in. So f of 900 is going to be the 1,000 grams times the 1/2. Notice that it's 1/2. This is going to be decay. We've said in the past that if the growth rate for, this is of the standard form, right? We talked at the beginning, a times b, to the x plus c. It's a more fancy model. Nevertheless, you'll notice that b value right here, we stated that if it's less than 1, it's between 0 and 1, it's decay. So this is very much a decay model because of that value between 0 and 1. So we're putting this in a calculator. For those of you that are not very good with your calculator, you need to become very good with your calculator. If we do order of operations by hand, we get this. And if I put this in the calculator or do the math, we're going to get 125 grams. This is how they find out how old things are, right? When they tell you they're like 1,000 years old, it's exponential modeling. Here's some data, and we'll probably end up practicing this quite a bit in class. So do bring questions. Here's a table that models the temperature of a cup of boiling water left outside in Antarctica. We want to give a function that models the data shown. So we're going to do a typical function of the form f of, let's do f of t, or f of x, t in this case, a times b to the t plus c.
Perfect.
Now recall that if it's decay, it's between 0 and 2, right? A is going to be how much you start with. And what we start with in this problem, if we look at the table, it's very important that when you have a table like this that you have a 0. Okay, you either have a 0 minute or a 0 day or a 0 hour or a 0 time or a 0 year. Okay? Because 0 is your starting population, quote unquote. So that's your A. And T is going to be just T. Because this is not a population related problem, we don't have any non-reproducing population. This is your temperatures. We don't have C for this problem. C, recall, is the value assigned to a population that exists but is not reproducing. Okay? So there's no C. We need to figure out this B value. How do we figure out this B value? Looking at the data, what happens if you take 70 and you divide it by 210? What happens if you take 23.3 and divide it by 70? So every minute it's decreasing by 1/3. Okay, so that's going to be your decay rate. Please, 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 when I give you these kind of problems, keep track of this. All right, this only works because, one, we started at 0. 0 is always a start. If you have a 0, that gives you the starting population. If you don't have a 0, you have to go back and find a 0. 2. Notice that we're not missing any data. It goes from 0 to 1 to 2 to 3, etc. If it were skipping data points, you'd have to keep track of that and make sure you find what those data points are so you can get the right rate. If this rate were growing, the numbers would be getting larger instead of smaller. Okay, so keep track of some of those things. But for our problem right here, this is a model that, this is the equation that models, or the function that models this set of data. Okay, and then finally, of course, the classic discussion of the giant panda, right? An animal who has been affected by deforestation in man, but it's also affected by its own ability to reproduce. So you'll notice that in 1998, after national surveys found a 50% drop in giant panda numbers, the Chinese government put into effect the Wildlife Protection Act. Now, even though some populations are seeing a growth, others are seeing a decrease. Okay, what does this mean? It means that, so whereas in the past, when we had a population growth rate of greater than 0, right, for the model n equals n naught e to the r times t, now some parts of the population are experiencing a decrease, meaning that the r value, the growth rate value, is less than 0, it's negative. So in other words, parts of the population are going extinct. Okay, and unfortunately, the damage is done, right? We have a less amount of population to begin reproducing. So even though our conservation is pretty serious at this point, if we don't have enough individuals to be reproducing to increase the population, then conservation doesn't matter, because conservation demands that the overall population growth rate is greater than 0. Okay, so it's kind of tricky, it's kind of sad, but just wanted you to be aware of what population growth rate really means, how growth can become decay, what this means to a population.
I think I need a hug.
Summary: mathematically speaking, what is the difference between growth and decay?